The key elements, nickel, molybdenum and chromium, which eventually enabled the development of the range of materials we now know as stainless steels, were all discovered in the second half of the 18th century. But it wasn't until the early 20th century that scientists actually began to explore the complex effects of these elements when alloyed with iron. In fact, in spite of the grant of a 1912 patent in Germany covering the production of iron-chromium-nickel alloys, the first commercial cast of any stainless steel was produced in Sheffield, England in 1913 by Harry Brearley. It is probably a much less appreciated fact that the element niobium, which was also discovered over 200 years ago in 1801, also plays a key role in the alloy design of stainless steels used globally in the modern era. Indeed, niobium has been of critical importance in the stainless steel development story for some 80 years, since it was first added in 1933 to stabilize early stainless steels against intergranular corrosion and weld decay. Before we learn more about the unique role of niobium, we must first understand the differences between the main categories of stainless steel, which have been developed over the years for a range of applications. The balance of the elements chromium and nickel in the iron matrix dictates the category of stainless steel which is produced. A Scheffler diagram, which is often used to select welding consumables for the fabrication of stainless steels, also serves to illustrate the importance of the balance between chromium and nickel. It is generally accepted that the chromium level must be above about 12% for a steel to fully develop the resistance to rusting which enables it to be classed as stainless. But the Scheffler diagram reveals that, depending on the precise levels of chromium and nickel, it is possible to produce steels which are martensitic, ferritic, austenitic, or indeed mixtures of ferrite and austenite. Steels in the final category are, for obvious reasons, known as duplex stainless steels. We will now examine these various products more closely and highlight the important role which niobium plays in each. Austenitic stainless steels. The global market for stainless steel now exceeds 30 million tons per annum and is rising consistently by about 6% each year. Over 60% of this is austenitic, with chromium in the 13 to 25% range and nickel around the 8 to 10% level. These steels are used for some housewares, hygienic applications, containers, industrial piping, and in some constructional applications. An area of increasing interest is the use of this class of stainless steel for reinforcing bars because of worldwide premature deterioration of concrete structures. Other classes of stainless steel are also used in rebar, for example duplex, in aggressive saltwater marine environments such as piers, or where the non-magnetic properties of the austenitic grade are unimportant. Stainless steels, and the austenitic grades in particular, can be produced with different surface finishes, from matte and satin to high gloss, and lend themselves to a special chemical treatment which, on flat products, enables a range of colors to be produced from bronze through black, red, gold, and green. This is of interest in certain architectural applications. On other grades, such as ferritics, the range of available colors is much more restricted. Austenitic stainless steels have high ductility and a lower yield strength than some of the other variants, and niobium plays a number of important roles depending on the specific application. Niobium has a large atomic radius and is capable of straining the austenitic lattice to such an extent that, in combination with its grain refining effect, due to the formation of fine precipitates of niobium carbide or niobium carbonitride, it significantly increases the yield strength of the austenitic grades. Furthermore, by mopping up excess carbon and nitrogen, it minimizes the precipitation of complex chromium carbides during heat treatment or welding. This in turn prevents local loss of chromium in the matrix, which can lead to intergranular corrosion, pitting corrosion, or welding difficulties. Niobium also plays a special role, sometimes in conjunction with molybdenum, in increasing creep strength through precipitation hardening in certain austenitic stainless steels intended for high temperature application. A typical niobium level in this class of steel would be 0.8%. Ferritic stainless steels. Ferritic stainless steels either contain no nickel or much lower levels of that element, and are therefore an attractive option and significantly cheaper. Perhaps not unexpectedly, ferritic stainless steels have properties similar to those of mild steel, with the exception of their superior corrosion resistance. They are less ductile than their austenitic counterparts and can be prone to brittle fracture. Whilst some variants of ferritic stainless steel contain more than 20% chromium, the two most commonly encountered alloys contain either 12% chromium or 17% chromium, with nickel content selected depending on the specific end application. Ferritic stainless steels account for about 30% of the global stainless market, and are also found in some housewares, boilers, washing machines, and in automotive exhaust applications. Once again, niobium plays a critical role in preventing intergranular corrosion, particularly following welding, and in the higher chromium variants confers good deep drawability to the material, thus increasing the range of components which can be manufactured. Fracture toughness also benefits, and in the 17% chromium variants, the recrystallization temperature is raised, providing more flexibility and generating remarkable strength-toughness combinations. As in the austenitic class, combinations of niobium and molybdenum lead to the production of high-temperature resistant ferritic stainless grades suitable for automotive and other elevated temperature exhaust systems. As already noted, ferritic stainless steels are much cheaper than their austenitic rivals, and when optimized have a very attractive combination of properties and will undoubtedly grow further in popularity in the years to come. Depending on the combination of properties required, ferritic stainless steels may contain from 0.12 to 1% niobium. Duplex stainless steels. The duplex grades are designed to have approximately 50% ferrite and 50% austenite in their microstructure, which produces a layered structure with a good combination of strength and ductility. Such steels are widely used in storage tank, pulp and paper, oil and gas, and desalination applications. They are ideal for harsh, warm, and humid marine applications. In spite of these advantages and growing usage, the duplex grades still only account for less than 1% of the stainless market. Duplex steels usually have chromium in excess of 20%, with nickel around 7%, and usually include molybdenum to confer additional strengthening and/or improved higher temperature properties. It seems likely that ongoing research will also eventually establish a role for niobium to add value to this specialist class of stainless steel. Martensitic stainless steels. As will be appreciated from the Scheffler diagram, the simplest martensitic steels, such as those originally produced by Brearley in 1913, have the minimum chromium level, about 12 or 13%, required to confer the stainless quality, and nickel at around 4%. They are hard and strong, with moderate corrosion resistance, and are often used for cutlery, turbine blades, and surgical instruments. Indeed, there are many possible applications for martensitic stainless steels in areas where hygiene is important, for example, in surgical and dental implants. Stainless steel has a smooth, easy-to-clean surface, which makes it difficult for microbes to adhere and grow. For normal applications, niobium around the 0.3% level is all that is required to confer the tempering and welding resistance referred to in earlier grades. But there is now an increasing use of precipitation hardening martensitic grades, and these use combinations of copper and niobium in a low-carbon martensitic matrix to provide very high hardness, while maintaining the stabilization effect and maximum corrosion resistance due to the prevention of chromium carbide precipitation. A typical level of niobium to provide these effects in the presence of about 2% copper would be 0.75%. Brazilian mining company Companhia Brasileira de Metalurgia e Mineração, CBMM, a producer of niobium, directly sponsor and encourage research on all aspects of the use of niobium in steels, including stainless steels, on a global basis. To mark the special milestones of the centenary of the birth of stainless steel and the 80th anniversary of the first use of niobium to enhance the properties of stainless steels, CBMM have decided to confer a special medal. The medal is to be awarded to the authors of the technical paper produced in the last 18 months, which, on the basis of peer review by a panel of international experts, has made the most significant contribution to our increased understanding of the important role of niobium as an alloying element in any class of stainless steel. This unique and prestigious award has been won by a group of Chinese researchers from the Chinese Academy of Sciences in Shenyang, China. In June 2013, on behalf of the authors, Professor Xinghong Lao was presented with the Stainless Steel Anniversary Medal. The medal ceremony was part of an important conference held in Sheffield, England, to celebrate the centenary of Harry Brearley's innovation. Their winning paper throws new light on the various factors which affect how the properties of 17% chromium ferritic stainless steels can be optimized by careful control of purity and niobium and titanium levels. One very important new observation which has been made reveals how niobium in particular enlarges the solidification interval during casting, which in turn leads to more effective grain refining with improved strength and formability. This development will further enable ferritic steels to penetrate the market currently dominated by the more expensive nickel-containing austenitics, for example in household appliances and construction. As in other stainless steels, niobium is also available to preferentially combine with carbon and nitrogen to suppress the formation of chromium nitrides or complex chromium carbides. There is no doubt that the next few decades will witness further remarkable refinements in the use of niobium in stainless steels, and that such developments will make a significant contribution to our more effective utilization of the world's resources. Ferritic stainless steels offer a more sustainable and lower-cost alternative to austenitic steels in a wide range of applications. Reducing nickel to either 0 or just a few percent, and microalloying with very small additions of niobium and molybdenum in a ferritic matrix has been demonstrated to produce stainless steels with properties equivalent to those of many austenitics in terms of corrosion resistance, toughness and formability. Thus, indirectly, the judicious use of niobium contributes very effectively to cost control and the sustainable use of important world resources. Niobium is uniquely beneficial in the stainless steel story, and CBMM continues to support and encourage development work which further enhances the use of this key element in niche areas where it can add value to specific products in a sustainable manner. The medal-winning paper referred to earlier is a remarkable demonstration of the effectiveness of this strategy.